Today we will be recording Chapter 6, Weathering in Soils, for the geology class at Gibbet Community College. I say weathering in soils, and when I say weathering, I actually mean two different things. Weathering can be defined as either weathering, which is the physical breakdown and chemical alteration of rocks, or erosion, which is really only the physical removal of materials. So weathering changes the rock somehow, and erosion simply moves it. The two always work in tandem with each other, but they are two distinct things. The Arches National Park in Utah is a fantastic example of weathering and erosion. This rock did not form as an arch, right? This rock formed, as we've seen previously, it's an igneous rock, I believe. And then the softer sedimentary rock that was in this hole you're looking at weathered and eroded away, leaving you with this cool looking arch. Cool. So let's go a bit more in depth into weathering. There are two major classes of weathering. The first one I'll talk about is mechanical weathering, or essentially the mechanical breaking of rock. This essentially turns whatever is being weathered into a sediment. Within mechanical weathering, you could have frost wedging, which has to do with frost and freezing, right? This is exact, right? You don't put glass bottles in the freezer for a reason. That's frost wedging. That same process applies to the rocks as shown here. And before we go any further, this weathering erosion chapter is a very good example of the uniformitarianism approach to geology. That being, if you see something happening today, that same process happened in the past as well. We actively can see frost wedging, pushing, pulling, altering the landscape, creating, right, these cuts and these channels as shown here. So if I see a mountain that has these same sort of cuts in it, I can assume, well, maybe frost wedging did that as well. Mechanical weathering works essentially by increasing surface area. I'm sure we're all more or less aware of what surface area is. The more surface you have, the more weathering you have. The more weathering you have, the more surface area is produced. Cool. Sheeting would be another example of mechanical weathering. Sheeting is the exfoliation of an igneous or metamorphic rock that happens at the Earth's surface due to the Earth's surface having less pressure. In this example here, we have a Pluton. We talked about Plutons previously. These are the igneous magma chambers that have cooled and solidified. Over time, the soil on top of this Pluton will erode away, and perhaps something from the Pluton will uplift it up. And when this uplifting occurs, the lack of pressure on that Pluton will cause the rocks to essentially break open and breathe a little bit, giving you this sheeting effect as shown here. This is a massive dome, by the way, so that Yosemite, if you squint your eyes, look very close to the left of this rock, you can see people climbing up steps, right? So this is massive sheet. This is a massive Pluton that has this onion-like structure on it. Salt crystal growth. Again, this is kind of similar to the ice wedge we saw before, and you probably understand how that would work. And of course, biological activity. I'm sure you've climbed a hill and seen a tree growing in a rock. What's the tree doing? It's cracking and breaking up the rock. These are 4 examples of mechanical weathering, essentially the physical movement of the rocks. Beyond mechanical weathering, we can have chemical weathering. This is, as the name suggests, a chemical breakdown of the rocks and minerals by removing, adding, or altering the elements that make up the geology. The major processes of chemical weathering include a dissolving or maybe an oxidizing. Dissolving is usually aided by some acid, and it's kind of what it sounds like, the rock dissolving in some way, shape, or form, given the soluble ions in the groundwater supply. Oxidation, this is rusting or tarnishing, right? Any chemical reaction which a compound radical loses electrons and decomposes in some sort of way, right? As I said before, Iron reacts with oxygen to form iron oxide. This rusting is a very tangible example of oxidation. So if you see some sort of rusting going on in a rock, that's because it's oxidizing the same way that these barrels would oxidize. The key connecting tissue between dissolving and oxidation, however, is water. Water plus, let's say, carbon dioxide can form carbonic acid, which would speed up the chemical weathering. And that water also contains the ions that induce both the dissolving and the oxidation. Weathering plays a big role in the end. As we noted before, water would also play a big role in the ice fracturing, right? Because, well, that's what water is. Those crystals from the crystal fracturing, that comes from water. And the plants are looking for water where they mechanically wedge and break off the rocks. So the vast majority of all weathering that undergoes on the earth is more or less primarily linked with water. Carlsbad Caverns, if you ever get a chance to go here, it is fantastic. But Carlsbad Caverns are the direct result of erosion, weathering, and water. Right? That's where the stalactites and stalagmites come from, is the slow drip, drip, drip of water over ridiculously long amounts of time. So let's talk specifically something that has a very big importance to a lot of the world. Granite. Granite's very popular. Granite's all over the continental shelf. Granite weathers. Specifically, granite can be attacked by carbonic acid, which is something we talked about before, carbon dioxide and water. When this carbonic acid hits, the hydrogen atoms are replaced with other atoms, and the granite weathers. The granite is weathered into usually clay minerals like kaolinite. And as we talked about before, kaolinite is a very soft, very light mineral. Granite's a very hard igneous rock, right? When you have your hard granite turn into essentially talcum powder, bad stuff can happen. Chemical weathering products include clay minerals, hematites, limonite, things of that nature. When granite is chemically weathered on top of kaolinite, you can get some quartz sometimes, dissolved silicas and potassiums, minerals coming out of it. A lot of stuff can happen. So, when something chemically weathers, what's the timeline that undergoes with this? Well, as shown here, this is a good example of explaining the physical change that goes out from the chemical weathering. And remember, this is also in conjunction with the physical weathering. So you got some rocks that, let's say, fractured via XYZ reason that we've talked about previously. Water gets in those rocks, starts chemically altering them, starts loosening them up, starts rounding them out, if you will, reducing the surface area of the rock. As this continues, more cracks are going to form, more water is going to be introduced to this rock, dissolving it down, oxidizing it, changing it around. You have these nice round rocks in odd locations because of situations like this, as shown at the Joshua Tree National Park here at the timeline picture. We see this stuff happen on a day-to-day basis, so we can assume, since it's happening now, it happened in the past. The idea of uniformitarianism. At work, every single day, exactly as being shown here. So, chemical and mechanical weathering can work in conjunction with each other to bust up, break down, change stuff around. The mechanical weathering aids the chemical weathering by increasing the surface area, and the chemical weathering aids the mechanical weathering by weakening the rock, allowing for the mechanical weathering to bust apart. These two always work in conjunction. They're a lot of times driven by some form of water, which is essentially doing both work at the same time. And it's the main reason the world looks the way it does. Cool. Let's talk some other important factors in weathering. First of all, we should talk about certain rock characteristics, such as rocks with calcite. Calcite is easily dissolvable in acidic solutions, marbles and limestones, for example. If you have calcite and you have something acidic, the calcite dissolves very rapidly, allowing the water to get inside the rocks that the calcite was once holding. Silicate minerals, another very common thing, right? We talked about that. Weather in the same order as their order of crystallization, meaning some silicate minerals weather more quickly than others. Olivine weathers very fast. Quartz does not. It's because quartz is more rigid, stronger, and more resistant to the chemical weathering than olivine. Just because the olivine and the quartz are essentially the same chemically, the same at an element level, does not mean they behave the same in every regard. Climate, of course, plays a big factor. Climate comes hand to hand with water. Warm, moist climates get a lot of rain, get a lot of weathering. Arid climates do not, right? Temperature, moisture, of course, will play a factor in that way. I think that's rather obvious. And we notice that we get different amounts of weathering, different amounts of chemical erosion, depending on where we are. We see the deserts have these big, large angular structures that don't necessarily appear randomly in rainforests. Differential weathering, talked about this a bit, but here's another good example of it. Since rocks vary and since geology varies spectacularly throughout the world, they weather and erode and decay and dissolve and move very much in the same way. Igneous rocks tend to be harder, more resilient to erosion and weathering. Sedimentary rocks tend to be weaker and more susceptible to these things. So, as shown here, we have the remnants of a volcano. This would be the sills, the dikes, the channels from a volcano, the magma that cooled, the leftover sediments and the leftover weaker geology that was once covering these cool-looking shiprocks is moved, eroded, dissolved, taken away via regular weather means, right? Rain, sleet, snow, what have you, leaving these harder rocks still standing. This is very obvious when you look at headstones, right? You could have a headstone that's made out of a granite that's a lot less susceptible to erosion in the short amount of time, or a headstone that's made out of limestone, which is calcite rich, dissolves a lot faster, and you can't even read the limestone. You can't read the headstone on the right that's made of limestone because it dissolved. The headstone on the left, good old Peter Sweat, still standing strong, right? All right. We talked about erosion. I don't get into erosion right now because we could talk about other things, but erosion, I'm sure you understand, right? Rivers erode things away because the water carries the sediments. Wind erodes things away because the wind pushes the sediments, right? Ice, glaciers move rock around. Erosion at a very basic level is very well understood. So we're not done for the day, but I want to, as usual, go through these kind of slowly. So if you're watching the YouTube video, you can pause it, try to answer these questions, give yourself a bit better understanding about that. Because the other thing I want to talk about in this lecture is soils. When I say soil, what do I mean? What is a soil? Well, down here we have a diagram of a common soil yield. Notice within soil, soil isn't just the dirt, isn't just the sediment. If you're a gardener, if you go buy soil from, the local gardening store, Walmart or something like that, there's different grades of soil. There's topsoil, there's garden soil, there's planting soil, there's manure, there's all these different soils out there. Because soil in and of itself is comprised of many different things. It's comprised of, yes, the mineral, but also there's a moisture content, there's an air content, and there's also an organic matter content that goes into soil. How do all these things come together? Well, they, of course, start with the parent material, right? The residual soil of the underlying bedrock. You can also get some transported soil that forms in place on the parent material from someplace else, from the erosions or the weatherings we talked about before. And then you sit there and you let the time go at it. You let the weathering, you let the rock cycle, you let the erosion take place, and the soil will form and develop based upon the conditions outlying, right? Of course, within that time, within that geologic process of time, climate plays a big factor. The more moisture in your environment, the more moisture in your soil, right? More organic matter in your soil. This is why deserts don't deserts don't have good soil, because they're missing the water and the organic matter components. Whereas, breadbasket America contains lots of high quality soils for that reason. And as, of course, if you give time and you give water, precipitation, and climate, and you let all these things work together, you're going to get plants and animals, earthworms, bugs, droppings, what have you, mixing in with the residual and transported soil, forming the ground we walk upon. And the flatter it is, the more it builds, right? This process shows exactly how this valley structure develops the soils the way it develops. You don't get a lot of topsoil and sediment in very steep locations, such as the top of this butte over here, because the soil simply rolls off the hill. Right? I don't think I need to explain that too much. That soil that does roll off the hill here from erosion or weathering, for example, gets deposited as unconsolidated deposits in the valley itself. And all this soil rolls and constantly is churned and is fed by that water and is fed by the plants and surrounding it and the animals dying, the carcass, stuff like that, giving you fertile stream deposits. Of course, the other side of this valley, you can also have a nice thick soil, a residual soil from the slow erosion of the bedrock that did not have the steep slope shown on the left to run the soil off, right? So we're looking at dirt. What are we looking at? What exactly is going on with dirt? When you look at it, we in the geology community, in the soil community, have a term called soil profile. This defines the zones and the differentiates the different soils from each other, and also describes what they do. The reason why you only want to bury, for example, your garden plants so deep, right? Why you want topsoil, why topsoil is called topsoil. This is an idealized soil profile, a picture showing you the various differences. The top soil of the top is called the O horizon. This essentially is your leaves and your dead carcasses and your animal poop, stuff like that. You lose some partly decayed organic matter, not actual mineral material in the O layer, the O horizon. Directly below all those leaves and dead creatures and poop and stuff like that, we have our A horizon. The A horizon is the organic and mineral matter that has the high biological activity component. This is where your earthworms live, where your roots take place, things of that nature. When you think of topsoil, you're thinking of the A horizon. That's the stuff you buy at Walmart, all right? The A horizon tends to sit upon what we call the E horizon, or the zone of elevation and leaching. I think I mispronounced that word, sorry. This is little organic material, and it's essentially a porous zone that the water flows through. The water enters the A horizon, and if you're lucky, you have a zone that the water can transport out into. Clays and stuff like that make up the majority of the E horizon. If there is no E horizon, however, then you enter the B horizon, which is the zone of accumulation. The stuff that flows through the A and E accumulates in the B horizon in the subsoil section. Once you leave the B horizon, you enter the C horizon, which is kind of where you run into bedrock. You're starting to have less soil and more rock and things of that nature. And then, of course, below the sea horizon is your bedrock. You're out of sediment now. You're on the standing, right? You're on the parent material. So this is a ideal profile. This is what, if you kept digging and digging and digging, you run into these individual layers idealized. You're always going to have A on top of B and B on top of C. E can exist, cannot exist as a step between A and B. That depends. And then, of course, below all soil, eventually you're going to hit your bedrock. Cool. So how do we classify soil, right? This is important stuff to know. Groups consist of items that have certain important characteristics in common, right? Soils are classified using a system known as soil taxonomy. Taxonomy should sound familiar from your biology classes in high school. The soil taxonomy includes 6 hierarchical categories of classification ranging from order to series. Again, this stuff should sound kind of familiar, right? The agricultural productivity of soils can be improved via fertilization and irrigation, right? Crop rotation was a very important step in the formation of civilizations as we know it. But you can also damage soils by not taking care of them. Anyone who's ever gardened knows that the most important part of your garden is the dirt you're growing it in. You take care of the dirt takes care of you. An example of the human impact that can have on soil would be a tropical rainforest, for example. You got a rainforest. This happens all the time, especially in South America. You clear a rainforest for logging, let's say, agricultural use. You want grazing land for your beef cattle. Got to get them Big Macs, right? The soils in the tropical forest are rather poor in nutrients and usually unsuitable for agriculture. You can't just chop down a jungle and place in a bunch of wheat and expect it to grow, well, wonderfully. That's because most of the nutrients in tropical rainforests are found in the trees, right? There's not a lot of give back into the soil because that's not how that cycle works. So you clear a rainforest and he's like, oh, there was a bunch of trees growing here. I'll plant something completely different. Obviously it'll work. Well, it doesn't. That isn't the way that game is played. And then furthermore, once you clear that rainforest, you're promoting the erosion because the trees that were holding down the soil now are not. And any soil you did have, any of this A horizon topsoil that you did have that was useful is being taken away because all those roots not in there keeping it in place. Resulting in essentially land that goes from being useful to something to being unuseful for anything. This particular picture, that looks like they're building a road, so not the best of pictures, but this is a very common occurrence. And it's funny that we still have this issue because we learned the importance of soil manipulation, soil development, 500-600 years ago. But somehow we want to chop down a rainforest and still expect all of our cash crops to grow there like it's no one's business. I said, when you get rid of the trees, you get rid of the roots that bind the soil together, you get soil erosion. This erosion can be, of course, be increased by slope or climate, what have you, but it's not a good thing because you lose your A horizon, you lose your topsoil, and you're left with your B horizon, which is a bunch of clays and things that plants don't want to grow in. Soil conservation shown here. This is essentially the idea of crop rotation, or the idea that we're going to think about what the plants are doing, how the plants interact with the soil, and then we're going to build our farms so that we can best build and grow and increase the viability of our soil. Here we can see crops planted in strips along contours of hillsides, taking advantage of the natural topography of the region, grass planted along drainage, things along that line. So that way, if you do have a heavy rainfall, you're not necessarily going to be losing a lot of topsoil and your plants aren't going to be taken away along with it. And doing stuff like this allows these individual farms to continue to produce and continue to grow year after year after year after year and not see a loss in productivity because their soil is consistently staying strong. And this stuff takes a while to also build. Something you don't necessarily think about, but that's the true statement. So this was a quick one. That's the end of weathering and soils. I will, oh, what did I just do? Oh, I just ended that. I'm sorry, let me share that screen back again. I will be, there we go. I'll stop the recording